Day 6, we'll take a look at the sequences that we've been studying for the past 5 days, and we'll review. Warm-up. For each sequence shown, can you find the growth factor, also called the ratio, or the rate of change, also called the common difference? Be prepared to explain your reasoning. So if we take a look at the first sequence, we can see that this is going up by 10 every time. So this is arithmetic. And that means we have a common difference, also called a rate of change. And that common difference is what it increases by every time, so we're adding 10. If we were to write so this is review, if we were to write the recursion for this, we'd have our first term is 5, and to find any term, we would take the term before it and add 10. So there's our recursive statement. The second one, it says, starting at 10, each term is 5 halves less than the previous term. So 5 halves is the same as 2.5, and if it's less than the previous term, then again, I would think that would be arithmetic, in which, again, we have our starting value is 10, and to find any term, we would take the term before it and subtract 5 halves, or I'll put 2.5. So again, if you're adding or subtracting a number, and subtracting is just adding a negative, that will be arithmetic. And again, it's arithmetic if you add or subtract the same number every time. And this looks like 25, but it's 2.5. All right, I'll take a look at the next one. This one looks like exponential decay. So let's take a look at what it's going down by. So this is 16, 8, 4, 2, and 1. And we can see that it's the numbers are half of the previous term every time, so this is geometric. If we were to write the recursion for that, we would say our first term, right here, would be 16. And to find any term, you take the term before it and multiply it by half, or you could say divide by 2. But again, when we think of geometric terms, the growth factor, the common ratio, we want to think of what are we multiplying by each time, and we're multiplying by half. All right, our next one, again, geometric, and you can tell because we're multiplying by 2 every time, this would be an example of exponential growth. So, and this should be a sub 1, not a sub n. So this is geometric. And our last one, we have this table. We have to think, how are these terms increasing or decreasing every time? And here they're increasing. And if you're not sure what is increasing or decreasing by, there's 2 things that you can do. If it's arithmetic, you subtract one term from the one before, and we should get the same thing every time. So for example, 0.4 minus 0.3 is 0.1, 0.3 minus 0.2 is 0.1, and 0.2 minus 0.1 is 1. So this is arithmetic. You could check division too and see if that works. So let's try that division. And if it's geometric, you would take any term, so I'll try 0.4 divide by the one before it, and we should get the same thing every time. So if I take 0.3 divided by 0.2, I should get the same thing. And you can see it's different, so we know it's not geometric. Instead, we're subtracting 0.1 every time. So this is arithmetic. I was using blue for arithmetic, wasn't I? Arithmetic. And the common difference is negative 0.1. So we could say, all right, the first term is 0. To find any term, you take the term before it and subtract 0.1. I can't really, oh, there it is. Subtract 0.1. So here we have 3 examples of arithmetic, 2 examples of geometric. And in that same vein, we're going to take a look at a card sort in class today. Oh, I spelled geometric wrong here. Oh. So in class, we'll be taking a look at a card sort. We'll be doing the same type of thing at our tables, which is I'll give you some sort of sequence in one of these different representations, and you have to figure out if it is arithmetic, geometric, and can you match it up with its recursion. Our second task, we'll take a look at this pattern. It says, here's a pattern where the number of small squares increases with each new step. Can you write the recursive definition for the total number of small squares, S sub n, in each step n? Okay, so we take a look at it. We have 1 square in this step. Here we have 5, Here we have 14. But if you take a look at the shapes here, it's increasing by a square each time. And so if you take a look, here's kind of the pattern. This is 1 squared. Here's 1 squared plus 2 squared. 1 squared plus 2 squared plus 3 squared. So you can see every time that it's increasing by, whoops, the step number squared. So this is step 2, and it's increasing by 2 squared. This is step 3, and it's increasing by 3 squared. So that's going to help us write the recursion. So we would say the first term is 1. To find any term, you take the term before it and add the step number, which is n, squared. So here's the recursion. If we were to graph this, you can graph the first 3 terms. So here's n, here's s sub n, the sum. So I just have the first 3 terms, and it goes up to 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Right, so 3 is 14. This is 5. Oops, it keeps erasing. This is 1. So here's what the graph looks like. It's not linear. It looks kind of exponential. But it says, is the sequence geometric, arithmetic, or neither? And I would say neither. Explanation, if it's arithmetic, you're adding the same number every time, and we are adding, but not the same number every time. And it's geometric if we're multiplying by the same number every time, and it's neither of those. We're adding by the step number squared, which increases by 1 every time. So I would say this is neither arithmetic nor geometric. So quick summary, and then in class we'll take a quick assignment check where we can use our notes, and it'll be on the first 5 days. It says we have now looked at many different representations of sequences. We've looked at arithmetic, geometric, and neither, and different ways to represent those. So here's an example, a list of terms. A list of terms is your sequence, your ordered list of numbers. This is arithmetic. It says right here, arithmetic. And it's arithmetic because we have a common difference. And that common difference is 3. We're adding 3 every time. So to check for a common difference, you just subtract one number from the one before it. And every time you do that, you should get the same number. If it's geometric, you divide one number by the number before it. And then every time you do that in the sequence, you should get the same ratio. So it says, what's the common difference or common ratio? The common difference is 3. We can display a sequence in the following ways. A table. Okay, so table, we have our term. And then we have the answer. So here the first term is 4, the second term is 7, the third term is 10, the fourth term is 13, the fifth term is 16. So there's our table. Our graph, you'd expect this to be linear because we're adding 3 every time, so we have that same slope. So here's n, and we'll say this is a sub n. All right, so 1, let's see, goes up to 16. Here's 5, 6, 7, 8, 9. Here's 10. I'll just graph those. So the first term is 4. The second term is 7. The third term is 10. The fourth term is 13. So you can see that would be linear. The recursive equation, we need a starting value. And then the rule. So we're taking, to find any term, we take the previous term and we add 3. So there's a recursion. You can say for n greater than or equal to 2, because when you plug in, you want your first term to be 1. So in class, I'll hand out an assignment check, and you'll have the rest of the hour to work on that. And then there'll be an assignment for you guys to practice on Delta Math called Day 6 Sequences Review.